You can build the most robust, highly indexed database in the world, and a single everyday human request will still cause it to fail entirely. Traditional relational algebra operates on strict syntax. A standard SQL query can filter rows by exact text matches, join tables using explicit foreign keys, or order records by numerical value. It executes binary logic. But ask that same database to find a retail location that best suits a millennial demographic's tastes, and the architecture breaks. The database encounters a logic gap. It possesses no worldly understanding of what millennial tastes actually means. It cannot process semantic nuance, evaluate qualitative text descriptions, or retrieve external context to satisfy the query. To bridge this gap, engineers have begun bolting large language models onto their databases, creating a hybrid approach known as semantic query processing. In practice, this integration is currently a chaotic assembly of ad hoc prompt engineering. Developers pipe raw table data into LLMs with unoptimized context windows, leading to severe token bloat, creating high latency and unpredictable data outputs. To build a truly stable semantic database, we have to stop treating the LLM as a chatbot. We must formally define its functions into a strict taxonomy of LLM-enhanced relational operators, or LROs, and optimize their execution through rigorous empirical benchmarks. We define an LLM-enhanced relational operator mathematically. It takes a relational data input and a natural language instruction, invokes an LLM to perform the reasoning, and outputs a strict materialized relational table. We organize these functions into a matrix. The vertical axis categorizes the operating logic: select, match, impute, cluster, and order. The horizontal axis tracks data granularity: cell, row, column, or table. Intersecting these explicitly defines operators like select column. Internally, the LLM select operator scans the entire schema of the table. It evaluates the semantic relevance of every column against the user's natural language requirement, dropping irrelevant data and outputting only what fits the criteria. Classifying the operator on a grid gives us a mathematical definition, but it does not tell us how to engineer the system for actual deployment. A theoretical taxonomy fails in production unless the physical architecture of the LLM prompt, specifically how the context window is packed with data, is explicitly optimized for that operator's logic. This brings us to context packing, the structural method of arranging relational data inside the prompt before we trigger the LLM execution. The standard approach is the LLM-1 architecture. Rows are extracted sequentially into an iterative loop for a binary evaluation, making isolated judgments with zero awareness of surrounding data. Alternatively, LLM-all expands the prompt to simultaneously ingest a massive batch. By utilizing global context, the LLM establishes a relative baseline. It can see every element in the dataset at once, allowing it to compare records against one another before returning a result. For complex database relationships, engineers deploy a third architecture, LLM-semi. It executes a semantic left join strategy, isolating one target record from the first table and comparing it simultaneously against an entire batch from the second table. The choice between isolated reasoning and global context dictates the cognitive capability of the model. Applying the wrong context architecture to an operator will cause the query to catastrophically fail. To prove exactly which architecture pairs with which operator, researchers built ElroBench, an empirical testing ground executing 290 distinct semantic queries across 27 real-world databases. We start by isolating the select filtering operators and the impute generation operators. This chart shows the benchmark F1 scores and token costs for row-level selection tasks. Across 3 major LLMs, the isolated LLM-1 architecture strictly dominates the results. The mechanism here is straightforward. Filtering and generation require precise, fine-grained derivation. LLM-1 dedicates the entire reasoning space to a single tuple, preventing the model from being distracted by surrounding data. However, when we test the match and cluster operators for semantic joining and grouping, a massive vulnerability in current industry systems is exposed. Most systems blindly apply the iterative LLM-1 loop to joins, evaluating data pairs in a vacuum. But looking at match and cluster metrics, the LLM-all architecture crushes the iterative approach in both accuracy and normalized mutual information scores. The isolated loop fails due to criterion drift. When evaluating rows individually, the internal logic for grouping slowly changes from row to row. The global context of LLM-all forces the model to maintain a consistent baseline across the dataset. We see an even more severe risk with the final operator, order, which handles subjective ranking. If you ask an LLM to evaluate data pairs iteratively, it frequently hallucinates non-transitive logic. It claims A is better than B and B is better than C, but confidently declares C is better than A. When this contradiction hits a standard sorting algorithm, the entire ranking system collapses. Utilizing the LLM-all architecture prevents this collapse entirely. By looking at all records at once, the model outputs a singular, mathematically sound ranking list. Applying a standard iterative loop to all semantic tasks guarantees failure. High-performance data architecture requires marrying specific LROs to their empirically proven context packing strategies. Refining operators in isolation is meaningless if they cannot execute together. The final step is pipeline orchestration. This top-down flowchart maps a multi-LRO system designed to execute a subjective query, like finding the best restaurant, across an unstructured database. Execution begins with a standard SQL select pulling the raw dataset. The data passes into the semantic layer, hitting the LLM_select node. Configured with the LLM_1 architecture, it aggressively filters using isolated reasoning, dropping irrelevant rows and vastly reducing the volume. The condensed dataset then flows into the LLM_order node. The system shifts to the LLM_all architecture, utilizing global context to rank the subjective criteria, before a limit1 command outputs the final answer. When multi-LRO queries are executed using these strict architectural pairings, testing shows that system accuracy reaches state-of-the-art levels of up to 86.67%. The future of enterprise infrastructure requires moving past the chat interface. Language models must become deterministic, optimized relational operators inside a formal data pipeline. To see the hands-on architectural implementation of these semantic database pipelines, head over to the Learn by Doing with Stephen channel. And for continued deep dives into data science theory and the shifting landscape of machine learning infrastructure, check out the Stephen Data Talk podcast. Full episodes are available right now on YouTube Music, Spotify, and all major platforms. You can find the links in the description below.